carbon dioxide. So that is why all the carbon dioxide which comes from the cement factory is a big concern. So a lot of CO2 emissions come from the cement manufacturing. One of the negative aspect as far as the cement is concerned. The coming to this economic impact. So this is one of the sustainability. The coming to the economic impact. What is this economic impact? Yes. If you take a country like India, it is a labor-intensive country. Okay, definitely you see a lot of labor. Okay, depend on this construction industry. Wherever you go, it's not like abroad and all. You see this abroad. Very few people. Everything is automated. Automation is there. Very few people work on this construction side. Everything is very automated. Whereas in India, we cannot do that because it's a labor-intensive country. Definitely, we need to depend on this labor. And also, the economic impact is definitely it provides a lot of livelihood to the citizens, or livelihood to the construction. Labors, the construction industry. And if you look at the scenario right now, India is a developing country, and in the coming 30 years, we are going to see continued industry. Definitely, there is a lot of honest, lot of responsibility of this construction, and there's a lot of demand for this construction materials and all, and there's definitely a lot of construction happiness, and it really creates a lot of livelihood to this employment. This is one of the economic aspects as far as the sustainability of the country is concerned. Next. What is the negative impact? The negative impact is, okay, poor construction materials with concrete can lead to a high repair and rehabilitation. So what is happening, right? A lot of construction is happening, we have to bail and balance that. So we want to have the structures in no time. Okay? We want to we cannot like in the olden days, like you want to see how many years it took for construction of Taj Mahal? Any idea? Taj Mahal construction, they took maybe 20 years. So can we do a building and do a construction for 20 years? You cannot do that. So we want the structures in no time, within 1 year, 1.5 years, 15 months. Okay, that is what with speed we are going. So definitely, when we are going with this high speed of construction, so definitely the speed and the quality will not go hand in hand. Definitely, we have to compromise somewhere. That is happening also. So we have, because of that, sometimes we have a poor construction practices. Because of that, we end up with a bad structure. That we end up with a bad concrete. And when the structure is bad, we cannot demolish the structure, we have to go for repair and rehabilitation. Definitely that will add another cost to the new structure. Nowadays we see this new brand new structures which are hardly 3-4 years old. You see a lot of repair and rehabilitation is happening to the structures. Okay? So this is one of the negative impact of the concrete. It's a wonderful material, but we're not using the material to the extent what we design. Okay, they're not respecting the concrete. Everybody is having the site being a man-made material. It's not like other materials. Like steel is a processed material, cement which comes directly from the factory. Okay, the concrete we are preparing. So it depends on the people, depends on the construction practices of the contractor who somebody is adopting these practices. If the bad construction practices are there, definitely will have a very bad structure. If the good construction practices are there, definitely will have a good service. And what is happening is the cost cutting. Cost cutting in the sense like somebody, let's say, a government project, somebody has tendered a project. Okay? One contractor is tendered, he got the award of the project, and again he submit to somebody, again that fellow will submit to somebody. So like that, there are 3-4 people that are submitting the work. The first fellow has to also have to make a profit, second fellow also have to make a profit, third fellow also have to make a profit. And the final guy who's executing the job, he also has to make a profit. So in this process, what is happening? They have to compromise somewhere. Where they will compromise? They will compromise on this cost cutting, and finally, it will affect the final end product of the structure of the what are the element, what are the product. So this is one of the negative aspects of the concrete, because we are not handling the product properly. If we are not managing we are not managing that, we end up with repair and rehabilitation. We are adding additional cost to this concrete. So this is one of the negative impact of the next. The complete social impact. So we have discussed about the environmental impact the concrete has. We discussed about the economic impact as far as the concrete is concerned. We discussed about the social impact. What is the positive impact of the concrete? It's a long-term investment that is within reach for most and provides security to the user. Definitely. Okay. So all these builders and all this and all, they are also buying a house and all is a long-term investment. If somebody buys an apartment, definitely will ask depreciation over a period of time. All these things will add up. So this is one of the positive impact of the concrete. Okay, they are going to achieve this in the coming years and provide security to the user as far as the concrete is concerned. The structure is there. We are not building a hut. We are not building a non-engineered structure. Okay, we are building a design building, engineered building. Definitely that will have some life and definitely that will have some security to the end user users. But what is the negative impact? Next. So negative impact is what? Okay, because you see this, a lot of urbanization is happening. A lot of people are migrating to towns or metros and all. There is a lot of impact on this metros. Definitely, a lot of people migrate to the nearby towns and the cities. Also, definitely, you have increased infrastructure for these people. Okay, and you have to build. What happens? All these are becoming concrete jungles. Okay? Jungles means everywhere you see. Go to some metro area, like you see the Hyderabad. Now it has changed the face of Hyderabad history. And studying there. The other thing is that everywhere the concrete are becoming. That is another problem. And the quality of the concrete is not achieved for the user. This is one of the negative. So when we talk, we give a lot of presentations here about concrete, these are doing but the same is not being reflected on the site actions. Okay? There is a lot of negative impact as far as the quality of the construction is. The coming to this, if you look at it, because because come to the sustainability of the concrete. So it's not only the environmental impact, that's what I want to convey. Okay? People say that sustainability means you have to conserve the resources for the future generation. That is not the only issue. The environmental impact. You have to see the economic impact of the concrete. You have to see the social impact of the concrete. So these three things you have to satisfy. Then I can say that I have achieved the sustainability as far as the concrete is concerned. Sustainability is not only the environmental impact, it includes the economic impact as well as the social impact. Next. So the sustainability success requires maintaining positive economic, environmental and the social impact. You have to have more of the positiveness rather than the negative what are we seeing. Then only we can achieve the 100% sustainability as far as the concrete is concerned. Okay? So these things has to be satisfied the whole. Yes, it should satisfy all the three. The environmental, the economic and the social. This is what I want to tell as far as this presentation is concerned today. We just scroll on what I said, what we have done in the research as far as this mineral waste, this mineral byproducts are concerned. So this is what we're able to see. So this is what the principles of concrete construction we have to use, like this is a budgeboard, wherever we go, that wherever we do the presentation, we say that we have to use less raw materials and energy on the whole line, reduce the emissions and the waste on the whole line, analyze the cost effectiveness of the whole line, analyze the social impact of the whole line. This is what I'm trying to look at. Being an engineer, not civil engineers, okay, is the responsibility is not the design. Design like you have the IS codes and all, everybody wants to know the principles and all, using the IS code to design it. But how best you are doing the design is important. Okay, is it really cost effective? Okay, that we have to see. Okay, that is very important. It's not only the cost of the materials which are using for the construction should be cost effective, and it should add more value to this sustainability. Rather than simply building a structure, we should see the sustainability goal, whether a structure is a sustainable structure or not. Whether this is what all these IGBC and all this, the people they can always talk about this. They always talk about this, how they achieve this green building rating, how they achieve the sustainability. They always do that. It's not only the materials, they see the energy, everything. Next. As far as the concrete is concerned, you have to use less clinker. Clinker in the sense, use less cement, more of mineral waste, what are we going to see. Okay? And you have to use more waste materials. You have to increase the useful life of the project. That's very important. Increase overall cost effectiveness. This is very, very important. So how best you are having, how to make the structures more cost effective, that is very, very important. And improve defect insensitivity. Okay? The defect will create the awareness, to reduce the defects in the market, will create the awareness in the people. Okay? It's not that I told you that construction practices, like it is a non-good contractor, he simply complete the job. So the time is the money for everybody, I agree that, but it should not compromise on the project. And once you complete the job, you know that the next day immediately when you do the form work, you see a lot of defects. The honeycomb in this. That insensitivity should not be there. We should not forget that we have to create that awareness among the people. So there are some of these principles of the concrete construction is concerned. Next. So like coming to that, like I already mentioned that work is more like after the concrete is concerned, how we can make the concrete more sustainable. Okay? That is one in terms of the development of the concrete, how we can make the concrete more sustainable. We have to use the fly ash of the slag. Okay? These are one of these two materials highly aligned with where I am working on. Okay? How does it help this? We'll see this. The more how can the waste are more uniform the moment you mix. This fly ash is a beautiful product. Okay? If you can able to use judiciously, able to use how we can use this in a proper way. If you know the properties of the material, know the properties of fly ash and all, okay, you get a very homogeneous and wonderful mix. Really, over a period of time, we have a better performance in terms of the properties and the constructability. It improves the service life, the durability subsequently once it becomes hard. Okay? That is the beauty of this products of this fly ash and the slag. It will reduce the increase the life of the structure, it will reduce the maintenance of the structure. And increases tolerance of the non-ideal aggregates, improves working conditions of the construction. This is so earlier, like I remember that when we were studying the MTech and all, when this fly ash cement, the slag cement come in the market, people are hesitant to use that. People say, what is that? It's an ash you are using to reduce the quality of the cement and all. But nowadays you see this, after 20 years, you go and ask somebody, give me an ordinary Portland cement, there's no ordinary Portland cement. You will be either a fly ash cement or a slag cement, PVC cement or a slag. So that is, and you are bound to take that. Otherwise, you cannot build a house. This is what the scenario we have come up with. So that is what the beauty of this material. Next. So I just thrown under some of the uses of what we have done at IIT Bhubaneswar, we did with slag, the self-compacting concrete. Yes, please. Now coming to this, if you look at, I want to show this slide. Why I want to show this slide is, if you look at the construction scenario in India, it's a rough introduction. Okay. I already mentioned that there's a lot of push to the infrastructure development. Okay. Now coming to our this thing, our cement consumption is much lower compared to the other countries, like the developed countries, like China and other countries. It's very much lower compared to the other countries. So then we get very low with respect to other countries. In figure we have 85, Asia now. Very low amount actually used for the infrastructure only, and 20% as opposed to 60%. Very few, very less percentage are using for the infrastructure projects. And this is what I told you nowadays blended cements and cements. There is a lot of without the blended cements there is no construction at all. Okay? Every cement we are using and the PVC and the snags. And what is the problem is, like we do a lot of research, like I'll show you the slides, we do a lot of research on these new developments and all in the concrete, but that gap is always there. Okay? We do a lot of things, it comes on the papers, comes on the pieces, but the implementation is not up to them. So there's a lot of gap in the research and the application. So we have to bridge the gap. Slowly, India, that is the problem. In other countries, what are the projects that we immediately implement in the field, the research. So that is, it takes a lot of time because the mentality is like that, they can take awareness. They don't use the product without the quality permission. So a lot of drawbacks are there as far as the Indian conditions are concerned. We have to bridge the gap between the research and the industrial application. Next. Now, coming to this, you see the cement itself was invented some, for example, in the year 1824. Okay. But if you look at the Indian scenario or the world scenario, not much has changed as far as the cement quality is concerned. But you see that as far as the concrete technology is concerned, it has progressed leaps and bounds. And you see this, if you know how to play with the materials, you know the technology of the materials. Let's say it's a concrete technology. You know the technology of the materials, you really play with the materials, and you can do whatever you want to do. You can model the product that will be a new product. So you can see it has progressed by leaps and bounds. The reason being, it's no more a pure cement. The complexity of the concrete is increased drastically. Okay, we are adding so much of things. Mineral admixtures means we are having a fly ash or a slag, whatever the mineral waste they used to buy products which are coming from the industry. We are using it as cement infrastructure material, and at the same time we are using the superplasticizer. You know what is superplasticizer? No? You know what is superplasticizer? The chemical admixture. That is also we are adding to the concrete. So see the complexity. It is no more concrete is no more a mixture of cement, aggregates and sand. Cement goes aggregates and the sand and the water. So you see in cement, we have cement and this mineral admixtures. And again, we have superplasticizer, so much of complexity is there. That has really changed the scenario of the whole project. Okay? That's why, because of this automation, because of this additives and all, we are able to realize very high strength concretes of the order of more than 20 megapascals and more than 150 megapascals. Without this chemical admixtures, again, we used to struggle to develop 35-40 megapascal concretes. So this has really changed the face of the whole technology. That is why, because of this leaps and bounds, because of this, we are able to have the contextual structures, okay, 80-story structures and 50-story structures. Higher structures are to be able to realize because of this new areas. Another thing is the waste utilization. We are using all this, the fly ash slag, all this construction demolished waste, so many things we are doing in the product. That is a lot of research is happening in the development of the new products. Okay? And the good part is most of the builders they are applying these products in the real environment. These things are slightly changed in the last 10 years. I'm happy to see that what we're developing, people are showing interest, okay? Especially the architects and all, to implement these products in the mainstream construction. That is how we're able to bridge the gap between the research and the industry. Next. So this is what the concept we talk about this high performance concrete. A little bit much word. Okay? High performance, high performance. Okay? What is this high performance? How we can achieve this high performance? So the new generated use can be high performance, can be a high strength and a flowable concrete. Any of the mix of these. Okay? High performance already you should have the highest durability for any fluids. In the 30 megapascal design, okay, it should have not only the strength. That's what I want to say that. Like if you design, if you see a structural engineer, you always design it as a based on the strength of the concrete. Okay, for somebody like who's nowadays you see this not only the strength, they are asking this what is the service life of this structure? How long this concrete will last? Okay, what is the service life? What is the life of this concrete? This is what people are performance-based specifications. This is what people are asking for all this nowadays. Okay, so those are the case. Okay, you are not depending on this only on the strength of the concrete. You are depending completely not only the strength, the durability and the performance of the concrete. It means intended service life. It means life of this concrete. Okay, strength nowadays with the present point estimates whatever it means to get a strength. And 25, 30 is not a matter at all. But the thing is, what is the life of this structure? Okay, subsequently after 20 years, 30 years, how long will it last? Will it last 50 years, 60 years, and all? That is very, very important. You can have all these issue concretes like high strength, you can have a flowing mesh concrete, you can have high strength, flowable and durable concrete, and it should be easy to use and it should be costly. Then you can come up with what are the products, what are you can make based on the need of the application. Next. So this is what we have designed it. Okay. So we have designed this slag. You see the slag. You know what is the slag? Is a byproduct of what? Steel industry. Okay. Steel industry. So what we have done is the beauty of the slag is it is though it is we call it as a waste, we should not call it as a waste. Please, we should not call it as a waste. We should call it as a byproduct. So the thing is like it's no more a waste, it's a byproduct. The beauty of the slag is also called as a GGB is also called it as a hydraulic cement. Because the thing is like cement, it is also having a line, CAO to next. So when you take a cement sample, you mix it with water, it gets hardened. Similarly, you take a slag, you mix it with water, it also hardened over a period of time. Okay? That is why we have this flexibility of adding this high volumes up to 90% because of the hydraulic property of the slag. And we've been able to develop a set of technologies compared to 120 pascals. We've been able to study on the durability and the corrosion aspects. Next. These are the concretes. Next. This is what we developed as self-compacting concrete at 90% different because you see this simply pouring the concrete in the form of, in the bowls, with the vibration on. Next. Some of the trends. So this is what you see. This you develop a design chart. You published also to develop a design chart. If somebody wants to go, somebody said that I want to develop a concrete. If I want to use a 50% slag in the cement replacement, okay, you can add a 50% replacement here, and you will be able to get a strength of nearly 70 megapascal. The lab strength. Okay, somebody wants to design, yes, this is what I designed. Somebody wants to use a 90% replacement, yes, you will be able to design a strength of nearly 20-25 megapascal. So this is what we designed that people can use this, and the methodology which is there in the paper which I published. Okay, you can adopt this methodology. You can take a pen and paper as per the methodology you can design it self-compacting. What are the concrete you want based on this design? Because this is how we can use them in the real-time applications. This is what we have done. We were able to achieve the beauty of this. We can get a strength of nearly 100 megapascals. Okay, 100 megapascals lab study with this self-compacting concrete. The other thing is, what is this? Lightweight aggregate concrete, disintegrated fly ash aggregates. What are these? What is this? Any idea? Can you come across this one? Huh? Any of you have you come across this word?
Sintering. Doing sintering to the finite grades.
Yes.
It's making a molds.
Yes.
Mold.
Exactly. These are, you see this. I said that's a lightweight aggregate concrete with single fly ash aggregates. Okay. These are in concrete. We have aggregates, right? What are the aggregates we have? Fine aggregate and the coarse aggregate. The coarse aggregate is made from rock. The crushed rock. Okay, crushed rock. You get they crush this. Go to the mountain nearby, so the quarries and all. They crush this to the pulses, sodium, and all. Okay, that is a natural aggregate. Okay, see that I think the day will come, government is going to impose a ban on that because it is creating an ecological problem. Okay, so what we need to do is we have to equip ourselves. We have to see that if government imposes a ban, what we do? We have to stop the construction. We should not stop the construction. Construction should go. Let's take it as a Mumbai. They say that natural sand. The sand is a natural sand. They said they imposed a ban on the natural sand. So what they will do? They have to look for alternate means how we can get a sand for the construction. You cannot stop the construction. Similarly, the day will come, they will impose a ban on this coarse aggregates as well. So we have to keep ourselves what we do. So these aggregates are man-made aggregates. Man-made aggregates in the sense we have developing these aggregates. We are developing these aggregates. Okay? And these aggregates are made from these waste fly ash aggregates, and they are very light in weight. They are very light in weight. Okay? That is why we call it as the lightweight aggregate concrete. And these aggregates, what they do is fly ash. They take the fly ash, 100%, like 95% of the fly ash they take. You know, in the ring of bentonite, bentonite, the soil mechanism and about this bentonite clay. They mix with 95% of fly ash and 5% of clay. Okay, they use a calcination, they use a what you call a rotating drum. Okay, and in this, once you rotate at a particular RPM, particular rotation, particular angle, particular RPM, it creates some pellets. Okay, the green pellets, and this green pellet should be hardened. So they are going to sinter it. What is the meaning of sintering? Sintering means what? Huh?
Exposed to temperature. Heat, sir.
Heat. We have to heat those green pellets at a particular for half an hour or 20 minutes, whatever. So when you heat this aggregate green pellets, it becomes hard. It becomes hard like this material. Okay? So this becomes a very light in weight. Why they are very light in weight?
Density.
It's light in weight.
Density.
Yes, because the density of the flash is much lower. Okay, it's very light. It's very light. You know, flash is light. Its specificity is very low. So that is why we get this very low density. Okay? So this is what there are a lot of lightweight aggregate. Emphasis is more on this lightweight aggregate concrete, which is like this. So lightweight aggregate concrete we have a natural aggregates, the manufactured aggregates. The manufactured aggregates are from this fly ash, the expanded slag. My interest is more on this fly ash which I worked on. So why this is important? Because India is moving. Okay, and if you look at the Indian scenario, because nearly 96% of the electricity generating is based on this coal-based thermal power plants. Okay, if we generate this electricity, we have to incinerate. We have to burn the coal. When you burn the coal, you get the electricity. Okay, all these power plants depend on this coal-based, all the coal-based power plants. So when you are burning the coal, what do you get? You get an ash, right? You get a seamless. When you burn it, so definitely, since everything in the population is increasing, there is a lot of demand for the electricity because all the people are moving to the cities and all, a lot of urbanization happening. Electricity also is required, and definitely
100.
that is RCC, about pure concrete.
2400. 400.
So if you replace this, what will be the expected density of the concrete? If somewhere around 1800, 1900. Okay. If the density of the concrete comes down, what is the density we have? The structure comes down drastically. At the same time, we can reduce the foundation process. This is what we are trying to do. And these are the benefits. The density of the entire conventional aggregate is conventional aggregate is this much. This is almost half of that. The only drawback of this material is the lightweight, it's porous in nature. It absorbs a lot of moisture. When it comes to the regular conventional aggregates, it's rounded shape, from pure fly ash. It's angular shape, this one from natural polish. This is what it is. And what is the advantage of this aggregate actually? The reduction of that reduced slowly. Okay? So at the time of designing itself, we can able to say the structure index and the concrete. When the 30 megapascal concrete density is 92,000 let's definitely all the density right of the element, the slab builders, the wall builders will be better come down drastically, and overall the foundation cost will also come down drastically. This is what improves, reduces the loading on the structure, improves the thermal properties because of the porous nature, acts as a good insulator. It improves the fire resistance as well because of the porous nature, acts as a good resistance to fire, and moreover it improves the durability as well. Okay? And of course, what is environmental benefits? Not using natural aggregate. Yes, we're not using this aggregate, so can we call this a sustainable concrete? Yes. That is what it is satisfying nearly all the norms of sustainability. The using the waste, economic, everything can be done. Okay? So we will call it as beautiful environmental benefits, so when we get to this material. And the beauty of this material is, if you look at a normal aggregate, this is what absorbs, it absorbs only on the periphery. But if you take a lightweight aggregate, okay, these are all porous aggregates, the water gets absorbed. So you see the difference between. In the case of this natural aggregates, okay, when you're curing this, only the top 1 to 11 will only get curage. Whereas this porous aggregates, what happens, that's I showed you the earlier slide, it has got an absorption of 20%. So that water extra absorption, we have to account for the time of designing the mix. What happens is when you mix the concrete, no, these aggregates will absorb that 20% of water less. Okay, it will absorb, you bring the concrete. After the concrete becomes hardened, okay, what happens? This water comes out from that pores. The aggregate which absorbs this water, it comes out from this pores, and what it does the internal curing. You understand? It does the internal, facilitates the internal curing as that is the beauty of this material. Whereas that is not the case in case of this conventional aggregate. Okay, so if you use this aggregate, it doesn't require any curing as well. It does this internal curing automatically because of this porous structure. That is one advantage of that. Obviously, once it does the internal curing, the pore structure will be improved. This is what the durability will be enhanced drastically. This is what we need to look at. Actually, very important. Difficulty is definitely any new product. When it comes to the market, when you implement a new product, you will have definitely some pros and cons. Okay, we should not look. We have some limitations. We have some advantages and disadvantages. We should not always look for the disadvantages. We have to see what are the advantages we have, and we have to move forward. Definitely, any product will have some disadvantages. Then we should not stop that product. Okay, we have to see how to sort out those difficulties when you are implementing the mainstream construction. Okay, difficulties. It absorbs a lot of moisture. Many people stuck here. Yes, that can be sorted out. It's not an issue. Vibration that can also be sorted out. Okay. The problem is nowadays the code has come out. Let me give you this very old slide. Now recently last year the code for lightweight aggregate concrete has come, and that is for single aggregate. The code has come in the Indian code. In the 914 IS 914. Correct me if I'm wrong. It's a single lightweight aggregate. So we have a code now. We definitely can go and convince the people. Yes, we have a code for that. We can use it in the mainstream. Okay. And the beauty of this is, see, in the general construction, what are the grades we use? We normally use 25, 30, 35, 40 megapascals in the mainstream construction. We're not going to design very high structure. Suppose the building is there, are you going to design at 80 megapascal, 100 megapascal, at 60? No, you're going to use 25, 30 megapascal. So with these aggregates, it's quite possible to develop this complex. So go and use them. You can see the benefits of this, to bring the benefits of this. There's the difficulties in the pumping. Nowadays, it is every concrete is being pumped. Have you seen how the concrete is being pumped? Have you seen the pumping of concrete? You don't see? How they place the concrete? The pumping the concrete site is somewhere here. Okay, you're making the concrete here. You cannot take the labor. Okay, you have to pump the concrete from here to there. So it's like a water pumping. You cannot pump the concrete. Sometimes you have to pump the concrete against the gravity up to the 100 floor also. These are some of the challenges we're having in the site situations where we sort out all these challenges. These are some of the concerns that can be sorted out. So we have done a lot of work like Bhubaneswar. See this, what you are able to see this? There are various concretes. All the concretes are showing a density of less than 2000 here. What is the density of a conventional concrete? It's 2400, and this is showing a density of less than 2000. It's showing a density of nearly 2000 only. Okay, and this is the thing is the strength to weight ratio is very high. Even the density is low, but are you compromising on the strength? No, we are getting the same 25-30 megapascal concrete. I am not compromising on the strength. So density is a less density, and we are achieving a good concrete which is required for my project. And we have to properly use this density when you are doing this application. When you are designing the structure, you have to incorporate this density structure. The foundation cost will be reduced. It is the beauty of this material. This is the future, I would say. We also try in the workability and all these lot of issues. We are able to develop high workable concrete. We are able to develop a strength to water cement ratio like a conventional aggregate. Somebody wants to use a lightweight aggregate concrete, you can use this design chart, the particular water cement ratio, you can develop design model concrete also. And this is what the crack pattern is. In every scenario, the aggregate gets cracked. This is what the failure pattern of the aggregates. This is what a conventional aggregate, if you take a core of a conventional aggregate, it looks like this. Okay? There is an aggregate, what is this? A lightweight aggregate which shows that. Because you already seen the aggregates, how they are all precise and aggregates. This is what the difference between the conventional and the lightweight aggregate concrete. And what is the difference? You see this water content ratio. This is what a conventional concrete densities more than 2,400, and this is somewhere around 2,000 and all. There is a density difference of nearly 400 kg reduction in the concrete density. Okay. And the reduced density, we will be able to model the product. The lab will be able to achieve 80 megapascal concrete. It is lightweight. The density of 2,000, we will be able to achieve itself 80 megapascal concrete by modeling in the product. So we have good products as well. You see this, you take a scene image, you take a fly ash, a porous aggregate, sorry, the single aggregate, see the microscope, you see a lot of pores are there. It's a porous material. That is why, because of this porous nature, there is a lot of water absorption is. It's taking an absorption of nearly 20%. But the conventional aggregate is equal to 1% absorption. This is what happened and this is what interface. What is the interface transition here? IT said, any idea about this?
Yes.
So it is a zone between the aggregate particle and the moderate particle. You consider it as a leak zone. Okay, that zone will be densified. So next is we have other cement like. Can you close this? Come out from there. Go to the folder. Go to that folder. Close this folder. I can do it. Second. Yeah. Earlier slide I showed you that concrete without a cement. The cement free concrete, the cement free concrete, you might have heard this word geopolymer concrete. Okay? There is no binder. The binder which you are using this cement concrete cement, that cement will be replaced completely by this industrial byproducts. These are the very sustainable product. So looking at, we call it as a geopolymer concrete. How we have developed in the lab. The thing is, like we all know this story. One kind of cement produces nearly 80% of the concrete ton of CO2. All these things will have a lot of concerns as far as the cement production is concerned. Okay. And what we have thought of, why can't we have a concrete, okay, which is a cement-free concrete? We're not using a cement. We have only this binders. So binders, we have this fly ash, slag, water, all these things byproduct, and we develop the concretes. We have concrete in quality as the geopolymer technology. Okay. So we have developed this technology using these different bases which are available predominantly in the state of West. So these are what you call the geopolymers. These are cementitious materials that do not require the addition of OPC. And they doesn't require OPC. And we have to look for all of these. We have to look for the materials, the raw materials, okay, the raw materials which are rich in silica and aluminum. A fly ash or a slag or a red mud. What is a red mud? The red mud is a bauxite, aluminum based. Fly ash is come from thermal power plants, slag from steel power plants. Red mud comes from aluminum based. This is a big concern in the state of Odisha. They have big NALCO power plant, sorry, NALCO aluminum plant, Hindalco aluminum plant. A lot of red mud is coming. There's in the mountains, you see red mountains there everywhere. Also, the aluminum. Now there is a lot of environmental concern on this concrete materials is network as a building material. We are developing various products with this. Okay, so we have to search for the materials which are in same silicon or aluminum. The precursor materials, what is a precursor, and we have to use some alkali activators, use some alkali activation, use some alkali activation, use some activators to develop this cement technology. So this is what we have to look for: aluminum silicate rich in materials, aluminum and silica, and we have to use some alkali activators. Okay, so on cement, what are the materials we use? Coarse aggregate, fine aggregate, cement and water. Here, instead of cement, we are using this waste. So instead of water, we are using this alkali activators. And we are going to come up with a product which is nothing but a structure, a 3D structure like this. Okay, that is why we call it the geopolymer. And these aluminum silicate materials which are predominantly available of the fly ash, GGPS, red mud, and beta. Where we use these materials, okay, and as this as a binder, and we have used as alkali activators to come up with a polymer structure. And what are the alkali activators we use? Hydroxide or sodium silicate, which two are the alkali activators which are going to silicate, right? And finally, we are going to come up with a product. Okay, there's something like this. Okay, we use these aluminum silicate materials, alkali activators, regulators, SP, to come up with a geopolymeric binder. Okay, which looks like a concrete, which is a concrete only. The only thing is the structure is different. If they're there in the concrete, what structure will have? Cement comes in touch with water, what is the reaction you get? Hydrogen. What is that you get? CSH gel and calcium hydroxide. You get a CSH gel there. Here you will not get a CHL gel, you get a different gel here. Okay? So this is what so ultimately that product is the concrete only, and it has to be here. So this is what we look at here. The details, GGPS and SI, there is activities. So water uses activators, and this is what, since no cement has been used, and we can find this word as the word sustainable concrete. Definitely you can find this word because no cement is considered the researchers completely. So this is what the scenario is. So first the dissociation of the silicates, aluminum silicates happen because of this sodium hydroxide and all this, and first it gets precipitated, it gets a hardened matrix, and this goes on over a period of time, and finally we get a product like this, a 3D product like this, silica, aluminum, silica, oxide, aluminum. This is what the scenario is. Okay. So this is what the difference is. Ordinary Portland cement of PSC. Ordinary Portland cement, what the raw materials we use is the limestone, sand, and other materials, limestone and the clay. Okay, and you know the silicates. And silicates, calcite, you get these 4 types of silicates: calcium silicate, calcium silicate, all these things you get. Once it comes in touch with the water, hydration takes place. You get a CSH gel and all this material. And finally, we go to measure the properties. What are the properties? Strength, tensile strength. Okay, and so the quantity. Whereas here, we don't have any raw materials. Okay, what we are using is the materials are mostly amorphous, the fly ash, the slag, water in material, which is silicon material. And we are instead of water, we are using water here, hydration. Here we use this alkali activators, and we have a geopolymerization reaction. There we have a hydration reaction, and this is what the here we have. Ultimately, you get a concrete only geopolymer concrete, and we want to measure the same properties what we measure with the regular condition. Okay, we measure the same strength, elastic modulus, Poisson's ratio, right? Got it? This is what? This is what in a nutshell. Cement, these are the raw materials, comes in touch with the water hydration, get this CSH calcium which is not, this ordinary quantity here. We don't have any raw materials, these are raw materials which are reversed, you get all these waste materials, waste byproducts. You use this alkaline activation. Okay, these are the precursor materials to this polymerization. Happens, we get a 3D reverse silicate structure. And finally, come up with the concrete also here. What are the properties we are going to check for the ordinary concrete? We are going to determine the same properties for reverse. So this is what we have done in our lab is we have used a combination of these 3 materials which are most currently available in the state of Orissa. This fly ash. There are around more than 30 thermal power plants. Okay. Why there are more than 30 thermal power plants in Orissa is this is rich in this mineral resources. A lot of aluminum plants, a lot of steel plants, all the plants are there. So how they will run? Government cannot provide the electricity for these big plants. They have their own power plants, captive power plants. Okay, 1000 megawatt plants like Jindal, big steel plant, he will have his own captive power plant. He will not depend on the power given by the state of Odisha. He will depend on his own power. So definitely, 1000 megawatt power plant, definitely he has to use a coal-based thermal power. Definitely he has to use a coal. Again, the waste comes. Like there are 33 thermal power plants are there in the state of Odisha. You see the amount of ash which is coming from. And how we can manage the ash. That's very, very important. So we have used the fly ash and red mud. I already told you. We have two, Hindalco and there is a Nalco. A huge amount of waste coming from the aluminum industry. From aluminum industry and the GG is, of course, you know, they use a combination of these three, and we have developed a product. We got a G11 product already. We created this product. This is what after that, once it becomes hardened, we show all the mechanical properties, all the properties which are relevant, which are required for a concrete, you consider as a structural concrete. Our emphasis is what whenever develop a concrete, whether we are really using a product for structural applications or not. That's very good. Understand? What do you mean structural applications? What do you mean structural applications?
Load bearing.
Not very sure what any element is
Structural.
elements are beam element, column element, slab element. There are structural elements, right? So we are designing those, right? We are designing those not. Yes. So we have to use for such kind of matter, but not for the filling material and all.
Yes.
So like regular column, not too much of a time. We did a lot of work on this. We developed all the products that we did in the lab. We got a reasonably good work community. That's some of the properties that we were able to design initially. We started to get from after that, we were able to design all this. We designed 100 megapascal geothermal plant. These are all these properties we have designed in the lab. So can you call this one as sustainable concrete? Yes. We can make these structures resilient also with this. We are working in the state of Odisha also to promote this project. This you don't understand. So this is what. So like what we did is, you see this. See this. What is this? Like for a conventional, please pay attention. For a conventional concrete, you know the strength to 1% ratio, right? And the strength of the concrete increases, the 1% ratio comes from goes up. Similarly, for a geothermal concrete also we have developed the regulation process. Okay? So instead of water, what we have is the AC per meter ratio. And the actual what we use here, reducing this binded fly ash, slag, water. The same we developed a concrete is suitable for that curve of this concrete is daily at 5 meters. Okay? So somebody wants to design a geothermal concrete, you can use this. If for a customer water and what are the methodology given by the paper, you can go to design it and start working in the labs. Right? There's a lot of applications are there. You can use this for the paper application, like the sleepers. You know what is the railway sleeper is? Yes, release of payment, release for a lot of applications are there for this. You can use for some cultural heritage, old monuments, rehabilitation also. This is what we do in the lab. A lot of work has already been done. We have developed a structure, again, we were able to restrict, we were able to get over 60 megapascal. Now, we have been able to we increase the research, like we are designing structures maybe more than 100 megapascals. This is about geopolymer, this is another representation. So last presentation another 20 minutes. Is it okay?
Okay, sir.
Finish sleeping? This is another base now. This is picking up, this is catching up. Have you come across this word technology? Recycle aggregate. Recycle, what is the meaning of recycle?
Crush.
Reuse the materials. Lot of waste is being generated everywhere. All buildings are demolished now. What you are going to do in this place? Where are you going to dump all this place? In India, okay, nobody bothers about this because we have a lot of mountains, everybody goes and quarries it. But in abroad, there is a lot of concern. We never quarry the aggregates. Yeah, there's a lot of this in abroad in India. So we have to look for, I told you already, government imposes a ban, what you will do? Like natural sand, they are imposing manual notice also. No natural sand, you have to use manufactured sand, whatever. Now suddenly they say impose a ban, don't use coarse aggregates, no quarrying of aggregates, what do you do? Stop the construction. You cannot, you have to use such kind of means. You have to use what material for use of recycling method. So that the construction should not be stopped. So this is what the recycling aggregate concrete. This is also a lot of research we are doing and there are a lot of projects also. So this is what if you look at this aggregates, the spreadsheet on the question of the original concrete from the construction demolished space, similar recycled aggregate, such aggregate can be defined on the course, demolished the buildings and the grid supports, 8-4 runways, within 8-4 runways very frequently, they keep on making new runways. They remove the new old runway, new runway, what do you do with the old runway? You remove the sports aggregates or whatever it may be, concrete road beds, all this. Okay, you have to recycle them, you have to develop this recycled aggregate. This is a big work because why this is different from the regular conventional aggregate? How this aggregate is different from the regular conventional aggregate? So these aggregates when you in the concrete when you remove the sports aggregates from the old aggregates, old demolished waste, so motor gets attached to that. You cannot remove that motor completely. Okay? So that is the challenge. With the small attached motor, you have to develop a wonderful concrete. That is a challenge. So how we achieve the challenge? That is also a challenge. There is also a big research going on now. So there's a lot of media like that increasing drastically the population density. And I told you the infrastructure boom. There is a lot of demand for the infrastructure development. There is a lot of demand for this construction materials. Cement demand will go up. Concrete, aggregate demand will go up. Financial demand will also go up. So how do we want to meet all these demands in the coming days? Government imposes a ban like this. We have to look for alternative means. So this is what the scenario is. So the population is 138 crores. We just crossed 140 now. Okay? 140 crores now. And this is the 40% of the population living in urban area. More population leads to more demand for the construction materials. And there is a demand in the study said by 2030 there will be a shortage of the building materials. So what you have to do? You have to meet the challenge. You have to work, all the researchers should work to meet that demand, to meet the challenge. Okay? To look for alternate sources. Then the government imposes a plan, what alternate sources are immediately available for me, so that my construction, my infrastructure construction, whatever it may be, housing project should not be stopped. So that is what we are looking for alternate means, looking for alternate sources, and this is what recycling aggregates like. Maybe sometimes you are demolishing a building, sometimes because of natural calamity, that comes and building of buildings, a lot of sometimes old buildings are going to renovate, or you will very old building, 30 years old building. What you will do? You are going to demolish, you are going to buy it, you are going to construct a new structure. So what you will do with this old building is recycle the size. The natural calamity is that whatever it depends on 460 happens, or what we want to do material. So all these things are look for.
Walls also.
Yes, walls are better than yes, very much true. And the scarcity of the natural resources is building up, and we are looking for alternate means, and we are looking for this recycling of resources. We will learn for engineering also. Reduce, So this is what in Indian scenario as of now, like yes, there is a demand, there is a lot of recycling materials in every city now. We have to optimally utilize all these to meet our demand. We will discuss much on this. This is what I want to spend some time here. This is what all of you please pay attention. The recycling, there's all these demolished waste, it goes to the recycling plant. Okay? So what they will do, they will recycle first, they remove all these sports aggregates. So that the water also goes in. Okay? In the first case, in the first scenario, what they will do, the job pressure it goes to impact pressure, and from there, this is what the required size is 20 and the sand and all they do. In the first case, what they will do, all these aggregates they remove from that the coarse aggregates, they remove the dust, they remove. After that, they will go for this level 1 type. They use this mechanical grinder. Mechanical grinder is like they keep all these coarse aggregates, they use this mechanical grinding. In this mechanical grinding, what happens? The main aggregate will be there, and the mortar which is attached to that will go away. Okay? So in the first scenario, the level 1 we get 40% fine aggregate and 60% coarse aggregate. Not much of water has been removed. Only a very limited amount of water has been removed. So that is very difficult to develop a concrete because a lot of water has been attached to the coarse aggregate. It's very difficult to develop a concrete. Now still further, how to remove that another mortar, extra mortar which is there in this. This is the first level, we get 60% and the 40%. Again I do this mechanical grinding. By using this mechanical grinding. What they will do with the mechanical grinder, they put this aggregates, they vibrate it, the motor will go on. So this only we are using this level 2. I can use the third phase also. Again I can mechanically grind. What I will do, I am getting 35% coarse and 65% coarse. Almost nearly 90% of the water has been removed. But why we are not using this level 3 aggregates?
Distress.
Huh? We are not using this level 3 aggregates because see, I am not using this level 1 because a lot of water is there. And here the water has been removed completely, but I am not using that. But I will go only for this level 2 only. Why?
It's supposed to lose the
Stand to
property.
use.
Huh?
It's supposed to lose the property of the aggregate at this stage.
What about you know the main aggregate? The motor has been attached. If you over grind too much of mechanical grind, what happens? The main aggregate which is there, no, that will lose its, that will become weak. If that main aggregate becomes weak, then it's a big problem with it. So I don't want my main source of aggregate should not be weak. So that is why I'm going only for this level 2 aggregates only. Okay, it is not making the aggregate completely weak. Okay, so level 1 will be too much, with too much of coarse, too much of water, it's very difficult to develop the concrete. So I'll go for level 2, a reasonable amount of water is there, and if I go for level 3, the coarse aggregate, the main coarse aggregate are 10. So this is what you see, all of you are able to see. So this is our main aggregate. Okay, this is the main aggregate, and this is a attached to it. In the level 3, if you go on doing a lot of mechanical grinding, what happens now? This main aggregate is there now, that will become weak. If that becomes weak, it's a concern. Okay, that means the aggregate is already a porous aggregate before you are using in the concrete. I don't want the level 3 aggregates because though the water has been removed, but the main aggregate becomes very weak. So what I will do, I will go with this level 3. This is reasonably okay, and the water is only some amount of water is there. I will manage with that. That is why you always go with this level 2 grinding. So this is what I want to convey. So we are going for this. Almost all the people in this recycling plants, they advise us to go with this level 2. Okay, what are the research we're doing with this level 2? So this is very important. Okay. So this is what the contaminants, of course, wherever we get this. That is what we have done is when we started doing this research, we find the sand outside recycling fines and the coarse aggregate of recycled aggregates. But the recycling fine, the sand is dusty. It's very dusty. A lot of all these materials are there, organic materials, this and all. So that's why I said we do not use this as a sand. We use only the coarse aggregate, and we are quite successful. And the sand, we use a natural sand only for the research. So there are a lot of other treatments also there to remove the attached water, but these are all expensive processes. The chemical methods and all is going to be very expensive, and it's not if you want to use in a mass scale, you cannot do all these exercises. Lab work it is okay, but in mass scale you have to go for this mechanical grinding only. That is quite cheap. This is what the advantages: reduce resource consumption, reduce quarrying, reduce landfilling area. A lot of other benefits are there. Use the recycled materials. This is some of the job. Another thing is like the properties are very important. That is why see what I want to convey here is this is not that I have a material, I can directly go and use the material. any material when you are using in a density construction or using for any as a development of a product, you have to understand the properties of the individual materials thoroughly. You have to do proper material characterization. Unless you do this proper material characterization, you cannot do a real work. You cannot do for a main development of the material. You have to do this proper material characterization has to be done thoroughly. So that is why. So what we have to do is, we have whenever you are inside the aggregate, thoroughly determine all the properties of this aggregate. The specificity you see somewhere around 2.6, and the natural aggregate is somewhere around 2.8. 20 years, 25 years already undergone some life definitely. Because this mechanical grinding time also, maybe the aggregate might be this weak, slightly weak. Bench density is almost nearly the same. Water absorption is more. Why? Because of the attached water, the water absorption is more like in case, same in the case of this fly ash aggregates. Water absorption is also more, that also has recorded for. This porosity is also slightly more compared to the regular national aggregates. Okay, and the separation values and all you have to determine. So what you use is a structural concrete to determine all these properties. Okay, you have to determine what is the abrasion value, pressure value, impact value, all these. If these values are falling within the limits of a regular conventional aggregate, what you will do? What you will do?
Replace this.
Will replace? Exactly. Again, what we do if the aggregates are nearly at par, the properties of the aggregate nearly at par with the regular conventional aggregate, you can go for 100% replacement. Remove the conventional aggregates completely and go for the 100% replacement. If the values are inferior to the regular conventional aggregates, you cannot go for 100% replacement. Maybe you may go for 40% or 50%. That R&D you have to do before arriving at the optimum result.
Sir, crushing method impact value is much more compared to the nature aggregates. How it is called?
Yeah, crushing value, yes, it's a weak aggregate. How to determine the crushing value? Okay. So, the more the crushing value, more weak the aggregate is. Understand?
Due to the porosity.
Yes, the porous because of the attached water and all. Already it has undergone some life. And what is the highest quoted value? What is the highest value for this? What is the as for IS 456? What is the limit for this? Crushing value should less than 30%.
Yes, no.
Less than 30%. So all the aggregates are nearly they may satisfy. They may not. If it satisfies that, you can go for 100%. Yeah, because of the attached water, more the attached water, more will be water absorption. Water absorption is because of more attached water. And this water and also this one specifically comes from the attached water. So these are the areas of most high water absorption. Coming to the concrete, yeah, I want to spend some findings of time here. Coming to the concrete, you always say that all of you please pay attention. Consider me as a teacher. Okay? So as I come to the concrete, you always say it's a two-phase material. Two-phase in the sense we have an aggregate phase, we have a phase phase, the mono phase. But truly speaking, concrete is not a two-phase material, it's a three-phase material. Okay, three-phase in the sense we have an aggregate phase, okay, we have a cement phase. Apart from that, we have another phase called the interfacial transition zone. Okay, which is a zone between this water phase and the aggregate phase. We have an aggregate attached by water. Okay, that phase between the water and the aggregate phase. Okay, then between that phase, we call it as the interfacial transition. That is the most weakest zone of the concrete, and most of the mechanical properties of the concrete are being dictated by this weak zone. In any concrete, talking about the conventional concrete, we have this weak zone. Before, in every concrete, we have this weak zone. Like in the case of recycled aggregate, what will happen? How many zones we have? You can see that. So this is what is the transition zone? It's a thin layer shell around a large aggregate particle. Okay, aggregate, weak zone after that water part, after this water phase. Okay, so this is it can be seen only through a microscope, and so water films around the large aggregate with the mixing. And it's a weak zone. I'm not going to spend much of the time. The beauty of this is transition and what is the influence of this. So compared to the other two properties, the aggregate phase and the water phase, the aggregate phase and the concrete phase, this transition zone, we have a more transition zone. You see this zone is just center of the concrete. It increases the permeability. It provides wide What is the behavior of the concrete? If you draw a stress strength curve of a concrete, it shows a non-linear behavior, right? Why can it be a non-linear behavior? It's because of this ITZ zone. Understand? It forms a non-linear behavior. Okay? And it favors the crack formation. This is the weakest zone in the concrete. And in the case of this recycled aggregate, we have, in the case of concrete, we have only one zone, right? Suppose you look at fresh concrete, the fresh coarse aggregates, you get one ITZ jet. But in the case of recycled aggregates, you have
Two ITZ.
two ITZ. We have the one old ITZ set, and once you make a new concrete, the new concrete forms another new ITZ. So you have two ITZ zones here. So that's the challenge of this new recycling. Okay? So that is what I want to convey. We have this new ITZ set, it's a old ITZ which is already there with the original aggregate, and this is a motor, and this is a new ITZ, the new motor, the new concrete. So we have two ITZ zones, we will strengthen those ITZ zones. Right? That is the challenge of this. Right? So this is a big challenge we need to look at. So this is on the computer side. I'll show you more. So now these are the concerns we have. We have got two ITZ zones. It has got some particular lines. Okay? And some sometimes you have this gypsum plaster and some residual water is also been attached to this coarse aggregates. And the concern is the durability. So all the development actually you have to see what is the long-term performance of this concrete. That's the biggest challenge in the next case. So barriers, this is what people are using now. There is no problem nowadays. I do know the demand for the construction material is increasing. Everybody wants the materials. Okay? There is having a severe shortage already. Okay? They are looking for all these alternate ways. The barriers you have some barriers, but people are nowadays not bothering. So demand is there. Nobody bothers about these barriers. They simply take the aggregates, whatever it will be there. In LNG and all, they are setting up the raw recycling plants. Okay? And they are producing the aggregates and they are using the mainstream construction. Nowadays, the government is also supporting them. Now the awareness has increased drastically. Now the technology has come up. Okay? And now everywhere has recycling facilities now. In Vizag also we have this Ramki to set up this recycling aggregate plants here. Okay? You want to do some address, you want to do some research, you can work on this. Okay? The standard is also going to come up very soon. But nobody is bothering about the standards. What are the standards we have with the conventional aggregates? We are using the same standards and we are just moving forward with this recycling aggregates. So we have done some, see the thing is like, we have developed, if you have the previous slide, we have seen the geopharma technology, right? Okay. We have used both aggregates as a recycling aggregates completely. Binder is also a byproduct. So everything is byproduct. We are developing the product, everything is a byproduct. So what more you want? It's completely sustainable. We developed the recycling geopharma concrete also. These are the three patterns. I've already told you this also has the porous network because of porous in nature. This is what the crack pattern is. You can sometimes because of the porous nature it also gets cracked. What is concerned is when you see about aggregate distribution, when you do this attention, you see the aggregate distribution of the indication is that there is no segregation at the beginning of the day. We have developed the SCC also. One of the challenges we have adapted the formatting of the ingredients. Because some of the properties we have all these things satisfy all the properties, all the capability properties. What we have done is the new product. We use cement as a cement recycling aggregate. Recycling aggregate is again as a cement recycling, we use fly ash slag as how we do our. So if I use fly ash as a slag and other materials, what happens is ITZ will be densified. It will reduce the weakness of the nitrogen. So this is what most of them are satisfying the properties. Thus it can be possible to have a high performance recycling SCC. My employment one is queries? Fly ash, GGBS, whatever you want, you can use that.
Sir,
No, but is the question is your sir? What sir is told is that? Or you want to your question is something different? The fly ash aggregate can it be used again? That is what is.
That we have not come to that stage yet. People have not used the fly ash aggregate abundantly. Once they do that in the future, you'll see that. You'll see.
sir, sintered fly ash aggregate. Sintered fly ash aggregate. What could be the cost compared to our normal aggregate?
That's a very good question. The cost is more. I spoke to some of these plant people recently from Mumbai, sorry, Bhubaneswar, there are 2 plants. I asked them, they said that for sustainability issues, see the management, sustainability issues, I said they will give the same, these single aggregates at the same price of the
Normal.
coarse aggregate. So why they are doing this? So they want the people to use these aggregates in the mainstream construction and sustainability. So the cost should not be the barrier.
Sir, any distributors, manufacturers for
Yes, here in Vizag it is not like Bhubaneswar it is there. Jindal is manufacturing, there are something called Inform.
we can import?
If you want, I can address the samples to you.
Okay, sir.
They will send you, you have to pay some transportation, give the aggregates freely, pay
Okay.
some transportation costs.
No, sir, for construction purpose, they transport and all.
Yes, they're already, I'll connect to one workshop, I'll send you that next month.
Okay, sir.
You all can come, more, have more light on that.
Sir, you showed about the properties of recyclable aggregate that should be satisfied for the replacement of conventional aggregate. Sir, but what are the fly ash and slag properties? And what are the tests we perform?
But I used methods are there, no? Slag, fly ash, slag, silica film, the IS code is already there. So you do the testing as per the code, if it is satisfying the requirements of IS, then use the
So it
concept.
is like same as a test on oxygen.
No, the test is slightly different. You have to use an IS code, I don't remember the code number, but we have a code for a slag, individual slag, not Portland slag cement, individual slag, individual fly ash, individual silica. Use that
Separate course sir.
separate code set for all the treatment.
So it should satisfy.
You have to use the testing as per the code.
Sir, also, sir, in sintered fly ash aggregate, the water absorption is almost greater than conventional.
Yes.
Sir, it should be affect the chemical reaction between cement and water.
That is what. So you have to determine the water fluctuation initially. And that extra water you have to account for at the time of initial one. Suppose you have designed like a regular concrete. What happens the water is then completely absorbed by the 20%. There is no water available for mixing. So the extra water you have to account for. That is why you can thoroughly you have to determine the water fluctuation. And very precisely you have to add that extra water at the time of mixing. That correction has to be done. In regular conventional concrete was in water absorption 1%. That correction we are going to do it at the time of main correction. When you are designing the concrete, you assume that all the ingredients are necessary conditions. But in the real terms, you have to know that the ingredients are necessary. You have to do the corrections.
ముందు ఇట్లనే 60 రూపాయలు వాళ్ళు కాదనలేదు కదా